In this video, we'll talk about using a shift register to expand the number of digital outputs on your Arduino. Here we will make 32 output pins while using only 3 pins on the controller. This is useful because even if you have a controller with many I/O pins, some are used for system functions such as the serial ports and so are not always available for use in your project. They can be difficult to connect because the Arduino pins are quite close together, and you want to save Arduino I/O pins for functions which require special capabilities, such as analog inputs, PWM outputs, and servos. Separating out pins using the method we'll discuss also has the advantage that the outputs can be powered separately from the Arduino, so you can power LEDs, piezo devices, and other things without contributing to the total load on the controller. The method used here is best suited to things which don't change very often, meaning less than 10 times per second or so. It's great for powering lots of LEDs, relays or the like on your layout, but it's not so good for things which require access to internal timers or other fine control, such as servos and things which require PWM drive. We will need 4 8-bit shift registers, some pins to make connections easy, and a prototyping board to mount things on. Here I have also a couple of LEDs salvaged from a dead piece of equipment and 2 1.5K resistors. Here is the Vero board layout, viewed from the top. Very few cuts in the underside tracks are required. They are shown here as orange lines with triangular ends. The integrated circuits are conveniently laid out so their output pins are on one side, with only one pin needing to be wired manually, shown here as the green wires. Data goes into the uppermost IC on pin 14, then out on pin 9 and to the next IC. Those are the short yellow wires. The clock and latch signals go to all of the ICs via the brown and blue wires. Red and black wires are used for power and ground. When using Vero board or the strip board of your choice, always leave a little loop somewhere to make it easy to clip your multimeter ground to the board. I use a little loop of wire soldered to the ground track for this. The circuit's very simple, and when it is all put together it will look something like this. The green LED is connected to the lowest numbered pin and the red LED to the highest. Since these LEDs are only being used to show the pin state and they don't need to be seen in challenging light conditions, 3 mA or so of current is enough. You will want the full 20 mA if you need them really bright, but that's not necessary here, and the less current we use, the cooler everything will be. Also, here the device is powered from the Arduino 5V supply. That's fine for illuminating 2 LEDs, but for more lights or other loads, you'll need to run it from its own 5V supply. Here is the output board connected to a Freetronics Leo stick, with the code flashing the onboard and extender board LEDs on and off. Now to the code. The top of the file explains what will happen and how to make it work in your particular situation. Here is where we define the pins used on the Arduino board, the data, latch and clock pins for the shift register, and the pins used for the onboard LEDs on the Arduino. Here is where we define the output pins on the extension board. The code is arranged simply to make the pin numbers appear as an extension of the Arduino pins, so that pins 68 to 99 are on the extension board. Here we define some parameters used in the code. Param state wait is the number of seconds the loop stays in each state, that is, how long each LED is illuminated. The setup routine is used to initialize the program before the main loop starts. Here we set the pins to being outputs, and we set the initial state to pre-wait. When the main loop starts, the system is in state pre-wait. After the timeout triggers, it jumps to red and beeps. When it's in state red, after the timeout, it jumps to green. When it's in state green, after the timeout, it jumps to blue. When in blue, after the timeout, it jumps to yellow. When in yellow, after the timeout, it jumps back to red, and the cycle repeats. The jump functions set the LEDs and move between states. Notice here how the LEDs on the extension board are handled exactly the same as LEDs on the board using the Arduino I pins. Only the pin numbers are different. Now we'll look at set pin, which is where the magic happens. The Arduino onboard pins can be written directly using digital write. The pins on the extension board are a little more complex. We store the value for all 32 pins in a 32-bit number. The bit write function is used to set each individual bit in that number. We then send all 32 bits out to the extension board, 1 bit per pin. The Arduino conveniently has a function called shift out, which knows how to send data to a shift register. However, it can only send 8 bits at a time. So we need to break our 32-bit word into 8-bit bytes and send each one separately. To do this, we use the shift left and shift right operators. We start by making a copy of the 32-bit word and shifting it 24 bits to the right. Now we have a 32-bit word with 24 zeros on the left-hand end. That's a byte, so it can be saved into a byte variable and sent out using shift out. The following lines send out the remaining 3 bytes. After all the data is sent out, we set the latch line to send the data out to the physical pins. This latch line is important because without it, as the data travelled along the shift register, the output pins would change in sequence and strange things might happen on your layout. The shift register has some extra circuitry to hold the old data until the new data is fully loaded. The latch line is how we tell it we have finished sending new data and the data can now be applied to the pins. You will notice that we set the latch line low at the beginning of the routine before we send any new data. As before, notice that this code does not use the Arduino delay function in the loop at all. The loop is fully non-blocking, so you can add more work into it and it will still run smoothly. It also has the important features of logging and a way to indicate a software error if one should arise. Here is the board installed on the back of the Tuckermans Bend layout, where it runs the power relays, crossing signals and other LEDs. The files and static images are available in the Google Drive.